So, we have been looking at historical climate change, where we looked at the forcings, and then we were just looking at internal variability, which is a big part of global warming. So, we looked at El Nino, and there is a separate module on El Nino as well. So, you can learn that in more detail. I was a little bit short here, but El Nino is seen as a perfect example of the functioning of the Earth system, where the atmosphere is involved, ocean is involved, carbon cycle is involved, biology is involved, and we will see when we look at the teleconnections that it affects global weather and climate. And we will also see when we come to modern climate change that actually El Nino can also have a fingerprint on global warming itself. So, the fundamental thing there to remember is that the ocean that has been soaking up heat during normal times or during La Ninas belches out that heat into the atmosphere. So, causes a mini global warming, but after an El Nino 1 year later things go back to normal. So, the ocean begins to take back that heat. So, unlike global warming, this heat is going back into the ocean, but if you have decades with many El Ninos, obviously that heat is going to build up, as we will see when we come to modern climate change. So, continuing with the impact of biology, upwelling, etc., that we were looking at, I was talking about the oxygen profile with the maximum near the surface because of photosynthesis, the oxygen minimum around 1 kilometer because of all the organic matter that falls and is respired or is eaten, and oxygen is consumed and CO2 is released. So, you can see that the nutrient profile looks this way, and we said the oxygen increases with depth because of the thermohaline circulation that is bringing near surface high oxygen waters to the deeper ocean. The terms that are also critical that have been mentioned here are the epipelagic, mesopelagic, bathypelagic, and abyssopelagic. So, epipelagic is basically the upper ocean, where you have typically enough nutrients and enough light. Within the epipelagic, often you have something called the euphotic layer. Euphotic layer basically means there is enough light for photosynthesis, which also tends to be about 100 meters or so. Mesopelagic is the middle layer, where there are various types of life, various kinds of fish, large zooplankton, and so on. Bathypelagic, where light begins to almost disappear, so it is dark. So, oftentimes we also split it into aphotic and dysphotic zone below the euphotic zone. And abyssopelagic is basically very dark, and there is life. You can go on YouTube and look for what happens to a whale body when it dies and falls to the ground, for example. It goes all the way to the bottom in the abyssopelagic, but there are lots of creatures looking like snakes and so on that feast on this huge amount of meat that falls with the whale. So, main things to remember: the oxygen profile and the nutrient profile. We add to that the profiles of total dissolved carbon, or what is often called the total carbon of the ocean. So, dissolved is basically because there are also particulate carbon matter in the ocean, that essentially what is photosynthesized and is breaking up into pieces when it dies or is being eaten is obviously particulate matter. So, the photosynthesized material which is close to the surface in the euphotic zone begins to fall down and is consumed and dissolved, and some of it survives. So, this is often called marine snow because it becomes white powdery stuff, and you can see that very little of it makes it to the bottom. So, if there is 100% production here, about 90% gets recycled within a couple of 100 meters, maybe 10% makes it below 1 kilometers, and hardly 1% makes it to the bottom. But this is still very critical because that is the carbon that is not respired. So, it is carbohydrate. Typical formula for that is CH2O or C6H12O6, and that is sugar or carbohydrate that is photosynthesized. Why is it important that it falls to the bottom? Because there it can get buried in the sediments, and that is what is the carbon that is sequestered away. So, either it is calcium carbonate or all the sediments we were looking at for past climate change signals and so on, that material is buried here. So, the carbon sequestration is very critical. And also remember that we always learn that photosynthesis gives us oxygen, but actually most of the photosynthetic material is respired. So, the oxygen is consumed and converted, the hydrocarbons or organic matter is converted back into carbon dioxide. It is this matter that gets buried in soils, lakes, and the ocean is important for maintaining the oxygen concentration, but there is plenty of oxygen. So, we do not have to worry about, as I said, also in the context of fossil fuel burning. Fossil fuel burning is increased so much that it does show a decrease in oxygen, but nothing to worry about. So, here is the oxygen profile again. This is the nitrate profile we looked in the previous plot, and this is the CO2 profile. So, you have to just be aware of the units being used. Here it is micromoles per kilogram. Sometimes it is also measured as grams carbon per meter cube, gigatons of carbon when we start looking at carbon cycle at global scales and so on. But the profile you must emphasize to the students is that the CO2 also, like nutrients, is minimum near the surface. So, there is a constant exchange with the atmosphere. So, it is like opening the Coke can. There is immediately an exchange of carbon dioxide between the place where the carbon dioxide concentration is high to the place where it is low. So, in the ocean we will see that there are places where carbon dioxide concentration is high. As we said, it is where the upwelling happens. So, this high carbon dioxide is brought to the surface, and that increases the partial pressure of carbon dioxide near the surface. If it is higher than the atmosphere, then the carbon dioxide will escape to the atmosphere. If not, it will go into the ocean. So, you can see that it almost looks like the inverse of the oxygen profile, except that the oxygen increases here. That does not show such a increase because the carbon dioxide is being brought down here as well as by the thermohaline circulation. And in general, the best thing to remember is that we keep talking about carbon dioxide concentration in the atmosphere in terms of parts per million by volume. That is called a trace gas. There are only trace amounts of carbon dioxide, nitrous oxide, methane. Methane is especially in parts per billion by volume. Why are they trace? Because nitrogen is 79% and oxygen is about 20%, argon is 3% and so on. So, compared to those, these CO2, methane and nitrous oxide are trace gases. In the ocean, on the other hand, there is plenty of carbon dioxide, there is very little nitrogen in the ocean. So, nitrate, which is a form of nitrogen, is often a limiting quantity, which means like our lawns need fertilizers, the ocean surface needs nutrients, nitrate, phosphorus, silica, iron and so on to drive photosynthesis. Nonetheless, there is plenty of carbon dioxide in the ocean, and it looks like the inverse of the oxygen profile. This is what you have to remember, because every time you think about ocean circulation, you have to be able to immediately connect it to the chemistry and the biology. So, the biology we looked briefly at in terms of the chlorophyll diagram. We have not looked at the details of how the seasonal production changes happen at higher latitudes, but there is a separate module that you can look up, and you can look at the animation that I showed in the first section of this course to learn about the seasonality. So, how do we relate these chemistry to back to the physics of what we know? So, we know that the North Atlantic has deep water formation where the water sinks, which means it is taking the heat, the carbon dioxide and oxygen with it as it sinks, which means if you go to the depths of the North Atlantic, you would expect more oxygen, more carbon dioxide and fresher waters. And that water that sinks is going south, mixing with the Antarctic bottom water and Antarctic intermediate water that is forming in the Southern Ocean, and is inundating the Indian Ocean and the Pacific Ocean. We said over hundreds and thousands of years that deep water is getting converted to surface water and coming back to the North Atlantic and other deep water forming sites. So, that should mean that there should be a signature in oxygen and carbon dioxide when you go away from the deep water formation sites. Obviously, that is what happens. So, if you look at the oxygen profiles, now we are using microliters or micromoles per liter, and here the CO2 is expressed as partial pressure, so microatmosphere, and we have not explicitly defined pH yet, but I think you all know what it is. It is basically negative log of the concentration of hydrogen ion H plus, which tells you about the acidity of the water. So, pure water is at 7, it is considered neutral. If pH is less than 7, it is an acidic solution. If it is greater than 7, it tends to be basic, and earth is typically remained at 8, 8.1, 8.2 for hundreds of millions of years. This is important because when we come back to modern climate change, we will begin to look at how the pH of the ocean is changing, which is acidification. It has consequences that we will look at. So, you expect that because of the deep water formation, the North Atlantic will have higher oxygen than the Pacific. Pacific has older waters. So, near the surface, photosynthesis, ocean atmosphere exchanges drive similar concentrations, but the North Pacific quickly becomes much poorer in oxygen as you go deeper. Okay? And it is the reverse for carbon dioxide. The biological production, again photosynthesis produces and the atmospheric exchange produces similar concentrations, and the North Atlantic is well mixed because it is pulling down this carbon dioxide with the deep water formation, whereas the respiration and so on are producing a much deeper oxygen minimum zone in the North Atlantic and a much greater concentration of CO2, which obviously would show up as much more acidic waters all the way down compared to the North Atlantic. So, this is how we begin to relate the surface circulation, upwelling, biological production and thermohaline circulation to the differences in the chemical properties of the different oceans. Let us look at just to touch back upon how the sea surface temperatures change. The normal situation would be, as we said, there is Ekman divergence or upwelling here because of the northeast and southeast trade winds. The waters are being pushed, piled up here and warmed up. So, we said the mean condition looks like this, where you have a cold tongue, a warm pool, and you can imagine what is here. That is where the winds come together, and there is another quantity called wind stress curl, which we have not defined yet. That generates warmer waters here as well, and that is where the intertropical convergence zone is. And as I mentioned, when we looked at the ocean color, this is what is called the meteorological equator. So, this geographical equator does not show up when you look at the winds, clouds, humidity and so on, precipitation, but it shows up when we look at the chlorophyll. So, if you look at the peak of an El Nino, this warm water is going to slosh this way. So, the entire ocean will look warm. This is kind of what we called the permanent El Nino kind of situation that happened 3 to 5 million years ago, when East Africa was much greener and chimpanzees and gorillas were walking on 4 legs, and then the conditions became like this. This is the modern mean state, over which now the El Nino is happening every few years. We said that led to the reduction in rainfall and aridification of East Africa. So, now this happens every 2 to 7 years. Upwelling is reduced, carbon outgassing is reduced, and this is called the anomaly. So, these are the total sea surface temperatures. We defined anomaly already in the first couple of lectures, where we said it is the deviation from the long term mean. So, if you look at December 97, normal December would look like this, but how do we know the normal? Basically, you take 20, 30, 40 years of December temperatures and you make an average and you say that is how the mean would look, even though this is for a specific year. Any deviation from the normal would be an anomaly. So, during an El Nino, you have anomalously warm temperatures here. By the same token, since the convection and everything move this way, you have anomalously cold temperatures here. So, you will have anomalously high rainfall here, mudslides and floods and so on, whereas here you will have droughts, forest fires, dust storms and so on. So, you can Google dust storms and you will see some amazing pictures from Australia where cities are being inundated with lots of dust like we had in North India in 2018, for example. So, let us slowly start moving towards modern climate change. To put all these things in context, let us just recap where we are headed. So, we came out of the medieval warm period, we went into a little ice age, and you can see that the reconstructions by various people using various different proxies of temperature like corals, tree rings, ice cores and speleothems and so on. The estimates vary, okay, but nonetheless you can see that the range of uncertainty or the standard deviation of the various estimates begin to get narrower as we get past the industrial revolution, which means the data we have for the more recent time is beginning to be much more reliable. So, within this context you have to figure out if the global warming is beginning to emerge out of the uncertainty and the variability in the past, and how much beyond the past it is going and how long back we have to go to find similar rates of warming and similar temperatures. So, we looked at very long time scale temperature records and we said that there is a 50 million year cooling, there is a last ice age, we are in a deglacial now. So, we were warming since the last deglaciation. So, we are still in deglaciation, but now within that we have this global warming that is definitely beginning to emerge out of the millennial or the last 1000-year climate variability we had. So, for all practical purposes we said agriculture expanded, deforestation happened and so on. Nonetheless, oftentimes we consider this as natural variability because human impact is not very severe when you go here compared to this period. So, the anthropogenic impact of man-made climate is now beginning to go beyond any natural variability we have seen in the historic period. Just to revisit the forcings, sunspot minimum also means radiation minimum, sunspot increase also means radiation increases because we have around the sunspot you have the plage, sunspot minimum, radiation minimum that contributed to the volcanic forcing during little ice age, and during the 20th century actually there is a what are called secular changes. So, these are secular increase, there is a decrease and there is a secular increase, and as I said before, people did claim that this increase in radiation forcing from the sun could be contributing to global warming. But now I will show that in the next chapter that satellite data is very good now and we can measure the radiation perturbation because of sunspot changes, solar variability, and that contribution is tiny. It is order 0.2 degrees compared to the 1 degree warming that we have seen during this period. Okay. Volcanic forcing, we said coming out of the medieval warming there was a burst of volcanic activity which was much more significant than the solar forcing for the little ice age. So, the solar forcing again added to the volcanic forcing, but the volcanic forcing seems to be the main cause for going out of the medieval warm period into the little ice age. So, there is again somewhat of a reduction in volcanic activity in the 20th century, but this remains part of the system. When we do global warming simulations and projections, we do want to take these into account. Obviously, we cannot predict how the volcanic activity will change in the future. So, we have to make some assumptions when we make projections about what kind of radiation forcing there will be. What does a volcano do? We already mentioned it, that volcanoes can put lot of aerosols, ash, dust, sulfates into the atmosphere, especially the stratosphere. Stratospheric stuff can remain there for a long time because there is no weather, there is no rain in the stratosphere. So, that is part of the story. So, the sulfate aerosols in the stratosphere are put in a huge burst by the aerosol when the eruption happens. So, if you look at time after eruption, the aerosol begins to decay away after reaching a peak. Basically, sulfates can produce things like sulfuric acid, or they can deposit on stuff, or they can just drop out of the air, what is called dry deposition, and so on, depending on how heavy they are, etc. So, when a volcano happens, a single volcano often is not easily measured, but there are things like 1816 or 1895, 96, when huge eruptions happened, and they actually resulted in things like years without a summer, where the haze and the dust was so heavy that temperatures actually cooled. Summers actually were so cold that crops failed, etc. But in general, how we figure out what volcanoes do is take multiple volcanoes like this and plot all of them from the time of eruption to the years that follow, and it shows that systematically all volcanoes have significant cooling for a year after the volcanic eruption, and the cooling begins to reduce, but it persists for several years. So, even though it is a pulse forcing, it produces significant radiative perturbation, and that is what gives us volcanic cooling. That is what is responsible for things like the little ice age, and it has been a player also in the past. So, on a long time scale, just to re-emphasize, this is the kind of CO2 balance. On geologic time scales, the volcanoes keep putting carbon dioxide into the atmosphere, and the weathering keeps pulling it down. So, even though humans are making a huge perturbation, once the perturbation stops, hopefully, the weathering will begin to take down the carbon dioxide that we have put in, but that will take a long time to equilibrate, and the temperature at which it will equilibrate does not necessarily have to be the current climate, because it depends on the radiation balance, as we will see in the next chapter. What are the other human influences that have occurred over time? So, this is an interesting figure, because it is showing the past 800 years or so of methane and carbon dioxide. And the interesting thing is that every time there has been massive depopulation or mortality among humans, either due to diseases or civic strife, wars and so on. Second World War killed many million people, for example, the Black Plague, etc. So, 10 million people died around this time in Europe and the Mediterranean region, 15 million in China. In the end of the medieval warm period, 30 million people died in China, about 25 million in Europe, and in more recent periods there were 50 million in America and 20 million in China. There is stories of how the Europeans and mostly the English colonized America and killed a lot of the native people. But actually it turns out that the diseases they brought from Europe to America killed more natives than weapons and wars. So, those kind of deaths show up as reduction in changes in methane, which is not as systematic, but there are reductions in carbon dioxide. How does that happen? Essentially, these are already very heavily agricultural societies. So, when such large depopulation happens, millions of people die, agricultural land tends to get abandoned. So, vegetation and forests begin to regrow, and those growths take up and sequester more carbon than agriculture would. So, agriculture is a seasonal thing where you grow crops rapidly and lots of carbon may be taken up, but you harvest them and eat them and so on. So, that carbon is released pretty fast, whereas when you grow forests, the trees grow, they remain for hundreds, sometimes thousands of years, and they can sequester significant amounts of carbon. Obviously, the signature is not as obvious, you can see a dip, but there are faster time scale changes than carbon dioxide, because methane in general has shorter residence time, plus when you have abandonment of agricultural land, you can also have swamps and so on, which can again begin to produce wetlands, swamps, marshes and so on can begin to produce methane. So, there are additional complications in the methane signature associated with. So, is this human impact? Well, yes, technically, but obviously not something like the global warming. I will conclude this chapter by pointing out to some of the techniques from the 21st century that are being applied to historic periods and so on to learn more about how changes happened, how ecosystems got perturbed and readjusted, and how these tools can be applied even for global warming and future projections, because these are the same models that are used to combine the climate science models together with so called human systems. So, there is always a natural system, which is the land, atmosphere, ocean, hydrosphere, cryosphere, which is ice, and then there is the human system. How do they interact? How do humans perturb climate, and how does climate make humans move or grow different things and so on. So, these kind of social or often what are called niche modeling, where the environmental parameters are used to look at how ecosystems are growing and moving in response to environmental perturbations and so on and so forth. So, they provide various kinds of information that is not obvious just by looking at individual data like this, for example. So, we guess that when humans died, agriculture was abandoned and forests were regrown, and we can go and find some evidence that in fact such a change happened. But beyond that, it does not say much more, but especially for the ocean and so on, you can do other things what are called network analysis. I will not go into the details, but it is essentially about how species depend on each other, walruses, salmon, groundfish and so on. And it shows, for example, the network analysis in the Bering Strait region has shown that marine food webs have been resilient to human predation despite variation in climate. I want to be careful, it does not mean human beings have no impact. It just turned out that there are places where the marine ecosystem is more resilient than we realize. Why is that important? Because when we go into modern climate change, we look at many negative impacts. For example, we will say corals are being bleached because of the warming, and the acidification or the reduction in pH is making the corals disintegrate. But what is the other side of the story? There are regions like the Red Sea or the Caribbean where some corals are responding quite okay. They are not dying. In fact, some of them are thriving in warmer waters. So, what are the differences in the corals that are responding well and the ones that are actually suffering? These differences might tell you things. What are the genetic differences? Is there a way to take the genes from a resilient species and put it into a weak species and so on? Such things are done. For example, jowar, some variety grows well in drier regions like North Karnataka or Marathwada, Vidarbha, but there are some that do only well in wetter climates, more rainfall. So, what are the differences? Can you combine them? And in fact, agricultural universities have done that, some with some success and so on. So, such information becomes very useful. Niche modeling shows that major episodes of construction and social codification each ended with reduction in maize farming. So, this region of US is typically very dry. Most of the rainfall is in this region, the so called breadbasket, but there is also now a lot of irrigation and so on. But California and so on, western US has been in a dry condition for a while. So, these kind of studies tell you how the climate and human activities interact with each other. There are other tools like agent based modeling, which means human beings are an agent, climate is an agent. So, there are differences, just the terminology is useful to know. You can read up more if you want. Anyway, agent based modeling shows that interhouse exchanges allowed larger populations to be supported temporarily in the face of climate change. This kind of information does not come just from a climate model. So, you need to take climate model which produces information that may have certain biases and uncertainties in them, and then human beings respond to it, and what is the net effect. So, these kind of modelings tell you that. There are trophic network analysis, species distribution modeling, numerical human dispersion modeling. You get very interesting information. For example, in India there is lots of labor migration, for example. So, depending on where the drought is, people will move, and oftentimes it turns out that they will move to a place where there is already a lot of water stress, and they move there because they think there are jobs there. So, you are just going to make the water stress worse in a region where migration happens because there is a water stress in another region. Climate models do not tell you that. Climate models just tell you that there is a drought here, but these kind of human dispersal models will tell you what are the responses that occur when climate perturbation happens. Those can be used together to create policies and ways in which to minimize the negative impacts or maximize the way to deal with the impacts, especially during disasters like floods and so on and so forth. Okay? So, these are kind of the different tools that are not directly physics based climate models, but what are called social models or socio-economic models and so on. So, this is a kind of a long chapter, but we had to make many points, and as we get into the modern climate, you will see that there are many more points to be made in terms of forcing, in terms of how we understand global warming, in terms of how we know what is human impact and what is natural variability and so on, and to also understand how to interpret what the models are saying about the future. So, there is a lot of terminology to be learned. So, the historical climate change, some of the take home points, that it is clear that climate change, East African aridification for example, was a major motivator for human evolution in terms of going from quadrupedalism to bipedalism, walking on all fours like chimpanzees and gorillas do, on two legs like we do now. Spread of agriculture has affected carbon dioxide and methane, no doubt at all, and anthropogenic impacts started basically at the end of the last deglaciation, because that is when large scale clearing of the forests and the expansion of the Fertile Crescent, expansion of populations and so on happened. And the sociological and anthropological impacts, of course, is that as agriculture created communities that did not move much, fertility went up, population grew, and so on and so forth. So, that net effect is that our impact on the environment began to grow pretty rapidly, but once the industrial revolution came, the energy consumption went up so much that the impact became very rapid and very large. So, human history has had fingerprints on climate change throughout the Holocene, and the main thing, as I said, is that the Holocene temperature changes have been less than a degree, and now we are already passing 1 degree since industrial revolution. So, we have to be careful how we have evolved and what our tolerance is or what our vulnerabilities are, and if we warm too much, what will happen. Evidence of the Little Ice Age is quite extensive, but it is rather limited. It is not clear that it was a very vast global cooling. Nonetheless, we know that medieval warm period definitely ended, had consequences like the disappearance of the Vikings, also the impact on Mayan civilizations and other civilizations in South America and so on. Since 1900s, there is unprecedented warming compared to the last 400,000 to 1,000,000 years that we can infer from the ice core records, and also more recent times like tree rings, corals, etc., tell us that we are warming quite rapidly and we are going past the range of natural variability that has happened for the past 10,000 years or so. The role of solar variability is low. It does not seem to be a big player, and all the good science now and the satellite measurements, which we will look at in the next chapter, tell us that solar variability may be a player in producing like a 11-year cycle in the monsoon and so on, but it does not seem to contribute to global warming. So, we will leave this chapter here and move to modern climate change, which is essentially looking more closely at global warming, which is the term that has now stuck. You can call it environmental change, global change, but people are already stuck with global warming. So, we will use that term in a loose sense, but essentially the terminology will have to evolve, include things like what do we mean by anthropogenic, what do we mean by global warming, and how do we claim with confidence that that is due to human activities. So, let us put that in the context of again some longer term things and look at the various evidences that have accumulated in terms of the radiative forcing. Remember that anything that changes the balance of radiation at the top of the atmosphere is kind of critical for climate change. Anything that happens within the system like El Nino and La Nina and monsoon and so on, they are internal variabilities. Okay? So, that is something we have to remember. So, one of the things that always comes up during global warming is global sea level rise. To put that in context, we know that the last ice age had huge amounts of 3-kilometer thick glacier growing on land, and we said when that much heavy ice is put on the land, the continents get pushed down. So, the bedrock that had been pushed down is rising since the ice melted, and there are bedrocks that are sinking ahead of it, because what was pushed down is coming back up, what was pushed up ahead of it is going back down. So, the ocean basins are sinking as well. Why? Because all that water that was locked up in ice is being released into the ocean. That weight of the new water that is being put into the ocean is pushing the ocean basins. So, that means the relative sea level has to be looked at carefully, as we will see. So, these are some things we have to remember. There are lots of old beach ridges that are now being exposed, and the elevation of the beach over time. So, going back the last 10,000 years or so to the present, you can see that the beach elevation has continued. That is the C14 dating here, you can imagine. What does that mean? So, if you think about the glaciation, when the water was removed from the ocean and locked up on land, the ocean crust would have risen because you removed a lot of the weight, and as the deglaciation happened, that water has flown back into the ocean and the ocean bedrock is being pushed down because of the weight. So, that means the sea level rise is going to be appearing less than it is. So, sea level is rising, but the ocean floor is sinking. So, the sea level looks like it is not rising as much, but you have to account for the drop in the ocean floor as well to know what is the actual sea level rise. That is something you have to always track, and it is not very easy to do. To put it in the context, if you look at the global sea level reconstructions, this is the sea level, and during the last glacial maximum going back, this is 50,000 years, you would have been lower because you are already kind of cooling from 50 million years ago. So, some with respect to the present, which is here, you would have been about 50 meters lower. As the ice age grew, you locked up lot of the ocean water into the glacier. So, you dropped the sea level by more than 125 meters, and the last glacial maximum happened here, the deglaciation started, all that sea level rise is because of this deglaciation. So, right at the end here where we are having, so this is stopping at the beginning of the Holocene. So, when we talk about sea level, modern sea level rise, we have to account for all these. How is the sea level rising because of the deglaciation, and how is the sea level changing because of the movement of the continents, whether it is ocean sinking and land rising or subsiding, and glaciers melting because of global warming and so on. So, you are talking about millimeters per year, sometimes centimeters per decade, and you have to be very sure that that is above all these natural variabilities that are happening. Very challenging, but we will see that the evidence is very strong that this is happening. As to global warming itself, if you look at the times and latitudes in the past 12,000 years where the temperatures have been above the current level. So, more than 2 degrees above pre-industrial in these red regions, above the pre-industrial by 0.5 to 2 degrees, or cooler than the pre-industrial temperatures. We will use pre-industrial as a kind of a benchmark because it is easier to say since industrial revolution began how much we have been perturbing the climate, how much warming is happening, how fast it is happening, what does it mean for various species, and so on and so forth. So, there have been many regions like the Nordic seas, Greenland, Southeast Europe, and Eastern China, North America, and so on, where the temperatures were much warmer. Why is this important? Basically because these were local warming, they were not global warming. So, I will show an animation which shows how the local warming and cooling have now become almost global warming. So, just at the same time there was warming, there were also regions which were colder than present. So, there were cold and warm patterns, like the little ice age may have been cold in one place, at the same time it might have been warm in another place, and so on and so forth. So, this kind of past variabilities are included when we reconstruct the past global mean temperatures. So, we will look at what kind of data there is for the modern times. We have been looking at paleo proxies and so on. We have to pay much more attention as to what we are doing since the industrial revolution to say what the changes are. We will stop here by again revisiting the fact that the natural modes or modes of internal variability, variabilities that are not related to any changes in the perturbation to the radiation balance at the top of the atmosphere. The most dominant mode that always comes to mind is of course El Nino, has warm temperatures here and colder, warmer than normal temperatures here and colder than normal temperatures here. There are several indices used to define El Nino. It's called different regions like Nino 3 and Nino 3.4 and so on, where there is warming, and those indicate that there was an El Nino happening or a La Nina happening. So, it is looking at the deviations of temperatures or anomalies with respect to the mean temperatures over this period from 1950 to 2015, and you can see that there have been many El Ninos, which some of which were strong, like 82, 83, 97, 98, the most recent one during 2015 and 2016, and there have been many La Ninas. There are many details. If you are an expert and you want to learn more, you can go and read up about why it is that El Ninos typically tend to be 1 year, 9 to 12 months, whereas La Ninas can persist for several years. There are reasons why that happens. We won't go into it, but at least you can notice that in this kind of construction, there are times maybe when there are more La Ninas than El Ninos or weaker El Ninos, and there are decades like the 80s and 90s when there were much stronger El Ninos and fewer La Ninas. All these sorts of things, as I said, will begin to also influence the global temperature trends. Okay. So, we will look at couple of more natural variabilities when we come back and keep building on what are the evidences we have for global warming, and then we will go to explaining what are the causes. But in compared to historical period, we will expand our information on the kinds of impacts into all spheres. So, we will look at the atmosphere, ocean, land, hydrosphere, biosphere, cryosphere, and humans' health, for example, and issues like water problems, etc. That puts the whole global warming in context, so that then we can move to what the projections are and what are the ways to mitigate climate change or adapt to climate change. See you next time.